cloud. Good, we're recording now. And share screen, share, there you go. So again, if you have any questions, please put it in the Q&A. If there's something general in the chat that you would like to discuss, if you have an opinion on something, please just put it in the chat. There is absolutely no problem with that. The idea of today is that we're going to be covering data analytics, data analysis, for what that entails. Specifically, how do we, prior to any programming language, prior to any tools that you're going to be using, what are the approaches that you should be taking? For your research, of course, many of you already know all of the stuff that we're going to be covering. However, many of you probably use some of the tools, but not of the ones that we're going to be talking about. So the idea of today is similar to yesterday. We're going to have a presentation covering the let's say, the backbone of data analysis. Afterwards, the plan is to show the examples that we have for today, introduce the other libraries for the web-based tools that we have developed, go over the examples that we develop in Python too, and continuous feedback from you guys, and also approaches that you might have that sound interesting. There's something in the chat right now. Okay. All right, good. So let's get started. I'm going to start with the slideshow. If there's any question, please let me know. And if there is something that you'd like to see also, please let me know. Welcome again, day 3. We just have one more day ahead. And the next day is all about, okay, what is the capstone project, right? So, okay, there's a question. Let's see. Could you explain more about how to retrieve data from sources beyond the list provided, and some sources like NASA data searches require login credentials? Okay, good. That's a great question. And we can do it in the example, but I guess I'll address it a little bit right now. Whenever you are submitting a data request to any of these resources, disregarding Hydrolang, disregarding the tool that you're using, there is an authentication layer that it asks exactly for the name that the REST API has been set up for. So the idea of the authentication is, in Hydrolang, you do it through, you put it in the parameters, if I'm not mistaken, either in the parameters and the arguments, but the name of the token that is required. By token, I mean sometimes you have a key, sometimes it says authentication token, sometimes it's just a token. So there's different names that you put in there, and you have to specify that in the request. And the username also should go in the request as well. And so since you're doing it between local developments, since you're doing it for your own, in your own computer, which I would assume, hiding this wouldn't be much of a problem, because you know exactly where this is going. If you're going to deploy it somewhere else, specifically, you're trying to connect with NASA data and you want to deploy in your web application, there are some ways in which you can hide that. And we can talk about that a little bit afterwards. There's a second one. Let me just read. Try to play with the USDS side. Wonder if we can filter station measuring certain parameters. Or Trubidi. Yes. So the example that we showed yesterday about Hydrolang was about streamflow. So what we're getting is USDS stations by streamflow, but that's not the only variable or parameter that is available either through Quasi or the USDS. So the let's say that the task would be on the user to see what is available within the resource that they're trying to access. Again, let's say USDS. I have nitrogen concentrations. but they're in a different temporal scale that I need. But if I go to the water quality portal by NOAA, I do have a different temporal scale that is better for my needs. So just change and take a look into what the resource has available. Usually the metadata you can obtain, just as we did before with Quasi, is you send this request for getting getting all the sites by box, and then that's going to include location-wise specifications, and so just plotting in the map is fairly straightforward. And for the station also, once you click on a station, you make the decision of clicking on the station, then making that request is just having something called an event listener within your web application, and you just click on that, and afterwards you make it. But once we can delve a little bit deeper into these questions afterwards in the training session in the second hour of the presentation. Any other questions so far? Sandbox, is there any other idea that we can run JavaScript on? Yes, thank you for that question. That's great, because let's see how we can approach this. So JavaScript is the language of the web, right? And the web is a lot of things. You can even deploy JavaScript in your phone. How do you do it? Is by these secluded environments in which all the runtime that is required for parsing and understanding what the instruction is, you have it right there within your application, within your device. So there are several ways of parsing JavaScript. What we're showing you right now is a client-side version. So client-side means in the web browser that you have installed, the web browser has an interpreter that is smart enough to know the instructions that you're parsing to it. And then through the different mechanisms that we have implemented in the libraries, we're able to extract several different features, right? So data connection, cleaning, sorting, all that kind of stuff. However, it can also be ported into a server environment, and this is where Node.js comes in. So Node.js is a server-side runtime environment for JavaScript, in which there's only so much you can do with the web browser in your local machine because of restrictions, right? We don't have a supercomputer, at least I don't have a supercomputer. If you guys have, you might be able to do much more. But many times parsing very large data sets, getting hundreds of gigabytes, even sometimes petabytes or terabytes of information, and extracting that information, you're not going to do it in your computer. But the runtime environment in Node, you can write JavaScript in Node and manage those large data sets. And then afterwards, you have the traditional way in which web applications are created, which is I have an interface, I make a decision, that decision is sent back to the server is running, let's say for this discussion, is running on Node. So it has a JavaScript interpreter, does whatever it is that is required to do, and afterwards sends a response, and response is just showing us on screen what we want to see. So that is another version. There are, I think, there are like 3 or 4 different runtime environments that are able to use. The good thing about this is across the board, you're able to run your JavaScript, and you're supposed to be able to run it almost everywhere. Why? Because this is standardized, so there's a lot of pull towards making it accessible everywhere in your devices. And so having the ability to run your code in Safari, Mozilla, Chrome, all the other web browsers or all the other environments is quite neat. And yeah, so we can have a little bit further discussion about this afterwards. Thank you for the question, though. And I guess alluding to what we talked before ending the session yesterday, we can go ahead and see how how VS Code can be used for the development of JavaScript code. and creating web applications with live servers and other stuff. Okay, so if there's any other questions, I'm going to go ahead and get started with the presentation. I'll be checking on the Q&A every now and then so that we can go back and forth. So any questions that you have, you can write it over there, okay? So data analytics, second day, very exciting because now we're getting into the nits and grits of, we already have our data, we already know the data that we getting from. Hopefully it's from a good resources. Hopefully, you know, we are getting all the features that we want to get from that information. And so the data analytics part has as primary objectives, further see what you can do with that data, right? So you need to clean it, you need to sort it, you need to handle different things that come with the information that is not necessarily at fault. Many times, sometimes these formats have layers on top of them that you need to remove, but these layers make it so that are compatible almost everywhere. So that's just part of the process, right? Correcting errors is a big thing as well. Seeing if you have NaN values, like not a number or null or undefined or any of those things. Why? Because through the cleaning, we are able to have more insightful and not biased or not incorrect information. So the data transformation and extraction for common data sets, that is one of the main tasks that we need to have for today. Performing basic and advanced statistical analysis for interpreting data. I know that, well, I say that a lot of us are understanding a little bit of the statistical process and the tools that we have available to ourselves. We're going to be covering some of them today as well, because the data analytics part is tied in hand with the statistics. We need to have some metrics to evaluate if our data sets are correct or not. And the next steps for that also include standardization, normalization, encoding, decoding, and that kind of stuff. So just to move forward, this is the same presentation that I gave, the same slide that I presented yesterday, the tools that we're going to be using for today. I'm going to be introducing two other libraries. So yesterday we were talking about Hydrolang. We're going to be talking a little bit further about Hydrolang too, but the other two libraries, HydroCompute and HydroRTC, which is HydroCompute for high performance computing on your web browser. So going back to the discussion of where I can run high performance computing, can I actually do it in my laptop? And yes, you can actually do quite a lot with your laptop. And the HydroRTC, which is the server side implementation of this. Both, well, actually server and client side. Server side, you parse and understand a lot of information, and you have that somewhere and you interface through a client side implementation. But we're also going to be using Python because I know that a lot of people are more familiar with Python on the processing side. We're going to be using Google Colab for the Python part. So I'm going to be sharing some scripts and some data sources. The online resources that we're covering is the StackBlitz today for the JavaScript parser. So yesterday we played with Code Sandbox. So I'm going to show you another one today, and also VS Code, so that we have all the spectrum of things, of tools available. The links for development, I think the presentation was uploaded yesterday. If it wasn't, perhaps we can, I'm just going to upload this second one anyway, and it has the same information, so that in the afternoon or whenever you have some time to take a look and see the resources that we're sharing with you guys. And today I will also be sharing just very briefly what Google Earth Engine is all about and how that those tools also are helping us do spatial analysis. Okay, so as an introduction for the data analytics part, we know that data analytics contains extracting relevant features from a set of data. So what is a relevant feature? Say that you have streamflow, as I'm right here seeing the Iowa River outside, and you get some streamflow data. And we had some quite a severe storm today. I want to see, okay, I want to make a prediction for the next week and a half or whatever. If I were to just look at today, I'd say, well, probably the river stage is going to be at the same level as it is right now, because that particular subset of data that I'm viewing as of now is just showing me the response from the watershed, right? Or the managing of the reservoirs, waters, up waters. So I need to know, for me to make a prediction, a full range of aspects from the data that I aim to understand. And that's where the relevant features parts come along. That's where the statistics come along. Am I putting and introducing bias into this information because I want to see what I want to see, or probably I don't even know what I want to see? And so the data analytics part is all about going back and forth with the process of, I know my information, I know that I want to create a model, I want to create something that is data driven, but I know that it's an iterative process. And going back to the data lifecycle, I put in here on screen the going clockwise, the data discovery, which we did yesterday, and part of yesterday as well with the data preparation. Today, we're going to grab that and put it in the model preparation too, and afterwards the model building, which is the iterative process that I was just mentioning right now, to afterwards create communication of results. How do you communicate results? Through visualizing cues, graphs, tools, web applications as well, something interactive. And there's one last part that I didn't want to put in here, which is putting this for production, because we're not using that, we're using it for research, right? However, it's worth mentioning. And what is the significance of the process of data analytics? Well, we're ensuring the data integrity and reliability. We're trying to see that the information that we're using for our models, that we're using for their processing, is good enough or understandable enough, or contains the features that we need to get, so that we can move forward and have a truthfulness within our analysis. Now, the impact of the data analytics process comes with cleaning data, how accurate the accuracy of this information, and it has an effect on the decision-making process throughout, right? So you have faulty that batch of data. Once you want to move forward into the next steps, if you haven't done all the pre-processing part in a correct way, you want to skip and you didn't realize there were some outliers that you didn't remove, then probably your model is going to tell you something completely different to what reality is. And through this whole processing part, we can simplify the whole integration of data towards the end use case. So again, it is imperative that you understand the problem at hand. It is imperative that you know what you want to achieve, but also explore the different data sets that you have available to your disposal. So the whole process of data analytics is, I know the data sources, I'm not just going to stick with one. If I have something that is completely reliable, or for instance, you have a reanalysis product that you are using, then perhaps you can just stay with that one. But I just have some stream gauges right outside here in the river. I don't know what's happening upstream. I don't know what's happening downstream. Probably it's best for me just to take a look and see if the information that I'm actually getting is reliable and quantifiable enough so that I can use it afterwards in my models. So starting with the nits and grit of the whole process, we have cleaning and sorting. So the process of cleaning and sorting is different techniques. The first one is handling missing values through the methods of imputation, removal, and interpolation. Removing duplicates by identifying and removing any values that have been repeated that are not necessary. So this part of repeating duplicates and removing duplicates is a little bit tricky, because how do you know that it's not a duplicate? How do you know that your data is simply just as it is? Say a good example is soil moisture, right? If you are depending on the accuracy of your measurement device, you will get probably the same measurement across a specified location. And so, do you need to remove those duplicates? Probably not. But is there any hindering issues that you might not see because of this data duplication and this information that is being repeated? Probably there is too. So it's always about, again, and I make emphasis on this, understanding what the data and the problem that you're trying to solve is all about. And from there, of course, we want to go and correct errors in the data sets. There are several techniques for you to do this error correcting process. Mostly it's just taking a look, seeing if it makes sense, and if it doesn't make sense, probably, and it has happened to me before, you go all the way into the model validation and calibration, and you see that it's not what you were expecting at all, and you believe that you have this great insight, but in reality, you just have faulty data sets. So going back and forth, and relying and seeing that it actually makes sense is critical step. So what is imputation? Imputation is a process of replacing data with substitute values. So by substitute values, I mean you have to either generate new values or see the underlying parts of your information. How you do that? Well, we use a little bit of statistics in here by obtaining the mean and median of the data sets that you have available. So I'm thinking about point data, but it doesn't necessarily have to be point data. Now, geospatial analysis, you have a shapefile that you're trying to get the, for whoever is using the shapefiles right now in GIS, the NDVI, so you want to get some vegetation, land cover usage or whatnot. If you know that probably there's an error with the satellite imagery that particular day, it wasn't in the process, there's ways of you correcting this, and it's basically applying these methodologies. Mean, median, then afterwards the mode, or perhaps using some regression analysis, perhaps using the neighbors around your data sets to see what they look like, and if they all look very much the same, probably the data sets that you're missing or the information that is faulty or problematic is the same as their neighbors. What are the advantages of this process? Well, you're trying to maintain a data set size that is not moving. So if you have 100,000 data points, probably it's not going to be a big problem for if you are missing some issues over there or some problems. But if you have a very small subset, and you know that your model requires this very small subset because the data is either highly variable or is very specific to that problem, then perhaps removing a couple of them is already removing from the accuracy of your model. It's simple to implement. It's just a mathematical framework. You utilize the formulas and afterwards you apply them. And there's, folks that use Python are all of these tools. GIS, it's just now a click of a button and just writing a couple of lines of code, and afterwards that's done. And it can definitely improve the model accuracy. Why? Because if you have a lot of variability within your data sets, that is not being accounted for by either readings or observations, then as I was mentioning before, models are just going to be doing or showing you things that is not a reality. What is the disadvantage? It can introduce bias, because not just because my neighbors like the color green, I like the color green, and I might have a lot of neighbors. So that represents something that you need to be always aware of. You might introduce some something that you don't want to put in there. It can reduce variability too. So if, again, if I have a time series that is showing me rainfall patterns across a basin, and I know there was an extreme event, but I know that in one particular hour, but it was raining the whole time for a very rainy month. And I'm saying, no, that's just a spike that probably was an error in the measurement device, then I am just not understanding the whole process of what. And with all of this, we might not be reflecting the truthfulness of the data. That is, I guess that's the smallest part, but actually, the data processing part, data acquisition part is all about how true it is what I'm doing. And the whole perspective of data analytics is you need to maintain the accuracy of the data that you have to the best of your abilities. So the imputation part is quite critical. The removal is, as it sounds, eliminating data entries that contain missing values. That happens a lot with the APIs that you find around weather services. So you're gonna see many of the sources that we showed yesterday contain information about just something on the top of my head, a rain gauge, right? And sometimes these rain gauges do not are faulty. You know, they're mechanistic devices. A battery might be off, a network sensor or something might be off. And so for a particular time span, when you require that analysis, it's just spiking up and showing you this very crazy value. So commonly, if something is not a reflection of reality, or the sensor already understands, or there's like a pre-processing part of the device sending data back into the server knows, okay, there was a misconnection, a miscommunication, so you just put minus 99999 or above, right, 99999, and it's just telling you, hey, this is not true, something happened. They might tell you in the metadata what happened, and many times they do have a specification once you read what is it that happened if a value is a certain number, but other times it doesn't. So it's always good to check up for that. And removing all that information if it's not reliable, that's you can go back into the imputation part again. How do you do this? By deletion, so removing entire records from missing values. Also pairwise deletion, so using just pairs for analysis, but that means how close am I in reality to the other data sets that I have available, right? What are the advantages? It's simple. It's ensuring data integrity throughout the data set. Disadvantages, it may lead to a significant data loss. So going back to that example of I have 100,000 data points that I got from an API. If I remove 100 of them, probably it's not going to be a big issue. If I have 100 data points that I got from that same data set and I remove 20 of them, then I might have a significant problem. So you're reducing the sample size. There is definitely some bias introduction there. So stuff to be aware of, right? Interpolation. So interpolation is the process of estimating missing values within a range of known data points. So the interpolation process, again, there are many ways of interpolating data sets. You do it through, I'm just listing here the most common ones, linear interpolation. So very simple. If I have my date today and date 4 days from today, have data for at least 4 to 5 days, probably the day that is missing, I can fit it within a single line. That's not going to be, it might lead to problems, yes, but that might be the best and correct way to do it. The other one is spline and polynomials, which is fitting within a piecewise polynomial. So you see that your data is not particularly fitting within a straight line, but you're able to derive a polynomial function that you can fit the data in within. So this is another process for doing it. And the time series specific. So time series is a tricky business on its own. and there are many ways of analyzing your information. And I'm just mentioning here backward fill, forward fill, seasonal decomposition. We're going to be talking about those a little bit afterwards too. What are the advantages of interpolation? Provides better estimates than simple imputation. Why? Because we have a more or less robust way of providing closer value to what was supposed to be represented. Now, disadvantages, it requires reliable underlying trends. So if you have large variability in your data sets, you cannot have, or I mean, you may, but I don't think it's the best way to approach if you have a 20 exponential polynomial fitting your data sets, because then you're just overfitting and then not great. And however, if you have a large data sets, you have a lot of information that it might be missing or missing in points. And this is very common when you're doing, for instance, machine learning or AI. When you're training these data sets, there's sometimes issues with the data itself. So it is computationally intensive because you need to apply through a lot of information, the same functionality, the same functions. Now, the process of correcting errors is all about identifying inaccuracies in the data and inconsistencies, of course. How do you do this? Well, basic things, right? Validation rules. So you know that your river network is not going to go above a particular threshold in steps at a time. You know the specifications of the device that is measuring that that gauging of the water. And so if you already have these validation rules, something that is falling outside of that probably is just an error, and you can just remove it from over there. Data auditing. So if you are managing large data from multiple sources or from multiple locations, doing these systematic reviews is actually set in place for many companies, for instance, that provide information. Statistical methods, so tests and algorithms that are checking continuously for outliers, anomalies. They use particular tests such as coming from Z-scores, standard deviation checks, and others. There's nothing like seeing a chart and seeing how something looks like, so visualization, to see, okay, maybe this doesn't make sense, right? Maybe I'm just missing a lot of information in here and I should be feeding something different. So visualization is crucial for these processes. And cross-validation by comparing across sources if the sources fall within the same scope, right? Fixing errors, the way you do it is manual correction, reviewing and fixing small data sets, automated correction by predefined rules, standardization, normalization, and recollection, which is, recollection is, I do not rely on this data whatsoever, so I might as well leave my sensor running for some time once again. Part 2, so pre-processing techniques. I see there is a question. Let me go back. Missing that says, should we always use interpolation or statistical analysis on numbers? Well, that's an interesting question because many times NaN is not a big problem, but it depends on the problem that you're trying to solve too. So if the data that you have is mostly NaNs, I would not rely on that data whatsoever, right? However, NaN might just represent an error within the reading or an error within the process that was generating that data, because we're talking a lot about observations, but many of these data sets are also coming from analysis from different groups, right? So perhaps the math framework that was being used for generating that data set in that particular location, simple polynomial fitting, it wasn't working, so boom, just put a NaN over there. And the crucial step is, I'm not saying you should always use interpolation. What I'm saying is, what is the problem that you're trying to solve? And having an and there, does that make sense to you or not? If you have an observation that is quite consistent across time, or you have a seasonal component to your observation, and you have a bunch of NaN values, probably that means something, right? So it's good to explore that. I wouldn't, again, I would never say, yes, always use interpolation. I'd say, take a look, right? Okay, I'll go into the pre-processing techniques now. What is it important about pre-processing? Well, we're trying to ensure that we have consistent data for the analysis that we're trying to perform. We are improving model performance by assigning and aligning data scales in different formats. And we have already handled prior, or we're handling within the system, missing values, outliers in categorical data. The ways we do this are by the following. If you have a lot of variability in your data, many times it's very hard to see if I need to do some pre-processing or post-processing. And standardization actually removes a lot of that, because what you're doing is grab the mean and the standard deviation of your values, and then you apply that throughout your whole data sets. So now you have a limiting set of values between 0 and 1, and that's easier to see than if you have, you know, -9 to 1,400 or something like this. Normalization is rescaling data into a fixed range, right? So similar to this, what we're trying to do is remove a lot of that variability, so that we better see if we need to remove or do some other processing to a particular sizing. And encoding, which is converting categorical information into a numerical format. How do you do this? It's simple. You know, you have an image. An image has 3 different colors, red, blue, green. And by me saying red, blue, green, red means 1, green 2, and blue is 3, then I'm able to remove the whole categorization by applying a numerical value. An example of the standardization that is usually used for processing is runoff in evapotranspiration, drought monitoring, and any other values as well from water quality control too. So going into the standardization, again, is scaling data so that it has a mean of 0 and standard deviation of 1. The way that you do it is you have all your data sets, you calculate the mean and the standard deviation, and for all of them, you apply this process. What is the use case? You have features that have different units or ranges. So you have a lot of variability in your data. You don't know particularly if that information is useful for you or not. And you're trying to remove that so that it's easier to analyze. It's common in normally distributed data algorithms as well. So this is very useful when you're trying to, and I'm going back to the machine learning, this is a very data-driven process. So it's very common also for that too. Normalization is rescaling data into a fixed range by applying the min-max. So this is a compound average, I think it's called. And the use cases for the normalization process is it's useful for computing distances between points. You can apply the neighbor algorithms, the k-nearest neighbors algorithms for normalizing your data sets. And it's usually used for, again, machine learning neural networks. It ensures that there's no single feature that dominates because of its scale. So easier to process. Now, encoding is the conversion, again, of categorical data into numerical formats. There are 2 techniques that I'm showing in here. Is one hot encoding, which you are assigning binary columns for each category that you have within your data, right? So an image. It has red, blue, green channels. And what I'm going to do is I'm going to create a matrix, and I'm going to assign within that matrix those values. Anything from there, it's easier to apply. From there onwards, it's easier to apply a mathematical framework, just I don't know, basic matrix multiplication to get more insights about this or similar. Labeling coding is assigning each category to a unique integer. So you have your a vector then that is you will know that you are using those numbers for those particular categorizations. And I'm going to go now into the data extraction and feature engineering part. So we normalize the data, we rescaled it. Now we are in the process of extracting some useful information from it. Why is this important? It's because we're trying to select the most relevant features for improving the performance of our models. We're trying to reduce the complexity of the data. Sometimes you have information that is highly complex. There's no need for that many times. And so removing many of these layers by just selecting the features that are truly talking, that are truly important for you is much better. And you're preventing overfitting. Overfitting is very common in the hydrological domain. I know that there's people who use we have a lot of folks that are doing different kind of things across, but it's a problem in the earth sciences because the whole process of model calibration, parameter estimation, it's very easy to say, yes, my data is correct. The information that I'm using for the performance of my model is correct. But in reality, there might be some overfitting process. How do you do this? Is by feature selection and feature engineering. So feature selection is correlation and mutual information. There's two different processes. Feature engineering is creating new feature from existing data. So what is an example of this is you have your satellite imagery, you apply some processing to extract through the encoding of these images, and then you are able to identify vegetation cover, imperviousness of the land uses, surface water bodies, etc. Now, what is feature selection? Again, we have correlation, which is it's measuring the linearity between two variables. And this is being done by the covariance between two different subsets. And the values for the correlation, if you have a high correlation, is between -1 and 1. If you have a very high correlation, it means that you have a strong linear relationship. What is a strong linear relationship? It's just rain in here in Iowa, and there's going to be an increase in the stream flow, right? That's something that is probably I'm going to have a very high correlation right over there. Mutual information is measuring information from one variable through another. So you applied this statistical, it's just probabilities, the probability that something is happening when something else is also happening, or given an event, if this the summation of these probabilities are higher or not higher. And if it's very high, then that means that you have a strong dependency between one and another. Separate example, you have large vegetation cover. You want to measure your soil moisture, right? Strong dependencies over there, depending on how much cover do I have, how much water am I going to find in the soil. Now, feature engineering is enhancing predictive power of the models through informative inputs. So this whole feature engineering part is its own presentation. I just mentioned some of the techniques that are being used. Transformation, which is applying formulas for transforming features. Sometimes seeing data in the raw format is not particularly useful, so you can apply different formulas. A Fourier transform many times for signal processing shows you way much more than if you're seeing the signal on its own. Laplace transformation, and so on, other mathematical tools. Interaction terms, so features that capture interactivity between the original features, polynomial features as well. This is going back a little bit into the interpolation part, so generating polynomial terms that capture the non-linear relationships. And this also alludes to the process of calibration models. Binning, which is transforming continuous features into categorical sections, and aggregation. Many times we cannot, and I think yesterday I gave an example about having the 2.5 meter DEM and having 100 meter DEM in an area that is mostly cover crops. Is it good that is it enough for me to have the 100 or the 5 or the 2.5? It's problem dependent, but probably since there's not much variability in my data sets, I don't really need to do much else, right? So aggregating information is that process on its own. Another one is if I want to do prediction of seasonality for 100 years, so comparing 1924 to today, do I need the information daily, monthly? Can I aggregate yearly? Can I do other types of aggregation? Probably, right? Okay, part 4. And there is some question. Let me go into the question. Okay, the question says, regarding missing data sets, afforestation, large number of missing data, then trying to fill a missing value could introduce bias. Yes. I think it's better to not consider such station. Is there any threshold that we could use? And if there's any data missing beyond this, then we could discard such stations. Again, I think it's problem specific. Yes, I'd say the top of my head, if you have other stations available that you can utilize, sure. But thinking of remote locations or thinking of places where data is not as readily available, many times you need to use some sort of interpolation for decision making. Again, what are we trying to do with the whole data analysis and data acquisition part is trying to solve a problem of when do I need to make a decision? What do I need to say, right? So it depends on the problem that you have. Quantify quality of data imputation. Beneficial if we could get these slides for some sessions so we can back and forth, touches and things. Yes, I am so sorry that I didn't share this before. We will share this data right afterwards. For tomorrow's, I'm going to share it before so that you have more back and forth about this. But definitely, thank you for the questions. And if anything, we can talk about them a little bit further. Somehow later. Okay, I'll start with the statistics and trend analysis part. And what does that look like? So descriptive statistics are trying to do summarizing information from the data that we're getting. And we're trying to describe the main features in a data set. So in here, I mentioned some of the key metrics: the mean, median, standard deviation, kurtosis, skewness. Are you trying to fit a distribution in your data to create some models? Are you trying to, is the information that you're having right tail, left tail? Is it pushing towards a particular distribution that you know that probably data is not fitting well? Those are the kind of things that we're trying to understand through the descriptive statistics, right? Inferential statistics, which is it's making inferences about population based on a sample. And with inferential statistics is a little bit, you know that the data is not bad, but not as reliable. So you need to make some testing on this information. This is the concepts of hypothesis testing, where you go ahead and say, okay, I want to see, I want to try something out. So if there is a feature from the data that I'm seeing and I'm asking, I'm getting that information, I set it up as either a null hypothesis, alternative hypothesis. You can use different metrics for evaluating. One of them is p-values, higher p-values, telling you probably there's good, you can use this information further down the pipeline. Setting up confidence intervals, which is from the population estimates that you have from the parameters, the range of values that you have are fitting within what percentile. How true is the information that I'm getting and moving forward, right? I have a 95, I have a 90. Many times it depends on the problem again, because 95, 98% is very high. Sometimes you don't have the data for accruing those confidence intervals. The next step is, and again, I know that there is many other things that can be talked about in here. I'm just mentioning the high level parts of the statistical section of data analytics. But I do want to mention, since we're using a lot of time series information, we're getting time series information from our APIs and from the data sets. I needed to mention data analysis, time series analysis, sorry, which is the process of getting data from points collected at specific time intervals, right? So there are several techniques that well, in almost all languages that are used for, not in almost, in every of the packages that are used for our domains, environmental sciences, hydrology, you have several of this information already there. Why? Because you need to understand seasonality, you need to understand backfilling, forth filling, and all of these techniques are readily available by just calling the function. So what I'm mentioning here is the composition, splitting data into chunks for trend, seasonality, and residual components. So my data point YT is the trend T plus the seasonality T plus any other residuals that I have. The other components and for the other tools used for time series analysis is autoregressive integrated moving averages and autoregressive moving averages. So in here I'm mentioning ARIMA, which shows the RMA, which is identifying patterns and forecasting. I'm going to show you afterwards how we're doing that with the hydro compute for data that we're retrieving from some of the stations. And what's basically that's doing is we set up some parameters that are fitting the current state of our the variable that we're observing for creating better predictions. Now, I'm going to shift a little bit the conversation from just talking about data analysis into the hydrological domain. Yeah. So what is model generation in hydrology? What we have is both predictive and simulation models. A predictive model is a focus on forecasting for future events that are often statistical in nature. We're going to be using a lot of the tools that we have discussed previously and many other ones that are not put in the presentation for creating some sort of a forecast to give us an idea of what might happen. We also have simulation models, which many of us already use in different kind of places, right? In which we have physical equations. We have equations that are describing the physicality of an event, of a process. So rainfall runoff processes, snow cover, snow melt, evapotranspiration processes as well, eutrophication, denitrification, and all of these that are quite well understood many times are quite complex too. Solving, and my domain knowledge is basically hydrology, a lot of hydrology. So solving shallow water equations. This is simplification of Navier-Stokes, because solving Navier-Stokes is quite computationally expensive. We need faster predictions. We need faster decision making. So simulation models are trying to replicate that process. And we're trying to understand the behavior under specific constraints, right? Constraints of data, constraint of temporal scales as well. And there's the coupling of the two. You have statistics coupling or aiding towards the simulation models. There's something else that I didn't add in here because I'm sure that by next year, there's going to be a lot of more input into the AI. There's the physically informed AI models, right? What is the importance of models? We're trying to do is risk assessment. So trying to make decisions at the right time by the tools that we're creating, the analytical information that we have in our disposal for flood prediction, drought management, resource allocation. And what do we do with this? Well, we have decision support for people who make decisions for many of us. So that means policymakers, your local stakeholder that has a say within the decisions of when am I going to get flooding in my neighborhood? Is it because it's tied up to something completely out of my hands, right? So how do you democratize information? How can you portray the importance of the information that you need to say? So trying to make the decision makers and people who are considering money-wise what is next step have an informed decision. And of course, understanding the system dynamics, comprehending the interactions within not only the hydrological cycle, atmospheric cycles, all these different processes. What are the different modeling techniques that we were talking about? Statistical approaches, again, regression models, linear regression, there's multiple linear regressions, logistic regressions, among others. There's decision trees, in which you take classification and regression trees for predicting what are the next steps, random forests through ensemble learning. So again, alluding towards the data-driven processes of machine learning. An example of this is generating a predictive model for flood risk assessment, correct? The other side is modeling techniques, so physically based approaches. There's 3 different physically driven approaches that we use: distributed models, long models, and the hybrid between the two. In here, I'm mentioning some of them: SWAT, MICHE, HLM. There's the National Water Model. There's all the suites of the HEC, right? HEC HLM for HEC HMS, HEC HLM, all this stuff. Long models, which is the simplification of the watershed or the units that we have into an equation that is making it easier to interpret and largely applicable across several use cases. And one of those is the Soil Conservation Service, the CN. And the hybrid models, which are the combination of statistics and physically based approaches to improve. Many times it's about improving the physically based outputs. Right, so the parameter estimation that you're taking, the parameter calculations and calibration processes many times are just put into a statistical framework so that it gives you a bound of a range of data that you can utilize then to inform your physical model. An example of this is the in-house, the hill slope link model that we have in here in Iowa for flood prediction. And I will be showing an example of that in the afternoon. Okay, I've been talking a lot about the wide range of applications of data analytics, and I want to stop right after this last example that I have for the case studies And these case studies are not necessarily just, something of, I know my data, I know the problem that I have, what is the process, the workflow that I need to take then, right? That's what I'm mentioning with the example case studies. And the first one is, again, flood prediction. What do I need? I need rainfall, I need a soil moisture, I need river discharge, correct? What do I need to do with that data that I get is a pre and post processing, so cleaning, pre-processing, getting feature engineering, the model generation. So that's all nice. Where am I going to get the data sources? Well, data sources can be for rainfall, NOAA. There are multiple products that you can get from them, LDS, MRMS. You can get observations also from USGS if you have good observations from rain gauges. The global precipitation measurements, which provide satellite-based data. Soil moisture is we can obtain it from NASA SMAP, which is global information, and USDA NRC for soil climate network. So there's a broad collection of networks that are informed across the world. What do I do then? I already get my data from the data sources that we mentioned before. So handle missing values, normalizing this information, getting features for moisture excess, rainfall intensity, like variables. And then I feed it in my model, which can be both physically based or statistically based or a combination, right? And then I can create a hydrograph that's showing me for a particular location with this set of variables, with this information, which on themselves can have some bias. But it's giving me an idea of what might happen in the next days, right? Another one, water quality analysis. So what are the data sources that I need? Measurements from water quality and weather data, right? High correlation. There's big rainfall event happening. And I live in Iowa. A lot of the nutrients going to be moving towards the streams. So I'm going to probably see in a couple of months or a couple of days even, a lot of algae bloom downstreams my river network, right? That are pre and post-processing, cleaning, pre-processing, feature engineering, all the stuff that we were mentioning before. What are the sources that I need? Well, for rainfall, NOAA, the rainfall products, water quality monitoring. If you cannot find from water quality monitoring from USGS, the EPA with USGS, they created the water quality portal, and you can get really good information from them too. And all these sources, by the way, are within Hydroline, so you can get that data from there. Again, data manipulation, handling missing values, normalizing this information, patterns, relationships, and obtaining statistics for your model. And then what can you do with your generated data is deriving insights from long-term change in water quality parameters, use time series analysis, moving average, and system decompositions for predicting the steps forward. And yes, so these are the two examples that I have. And now I'm going to go into Q&A if you have any questions before we go to our break. We're going to have another 10-minute break. And we can have it at 11. Well, it's 11 here, 11:10, so in 2 minutes. But if you have any questions, please ask away. We're going to start afterwards with the programming part. So I'm just going to be waiting for any questions right now. Open discussion as well. You can raise your hand. You can, yeah. Okay, well, since I'm not seeing anything from over there, at the next hour, we're going to have the training. Well, in 10 minutes, we're going to go a little bit deeper into the training part. The main focus, we can do the VS Code right now before the lunch, and show you how that looks like. Oh yes, something that I'm going to share right now with you is these here. Yes. So these are some for everyone. Some Python scripts that we created for that, we can take a look and step forward afterwards for getting data from two different products from NLDS, an NetCDF file from an HDFI file, and another one is the example that we had yesterday for USCS data retrieval, and getting some insights about that USCS data that we have. And I think I'm going to stop the share right now so that we can have the break. And hopefully I'm going to see most of you in 10 minutes. So going into the, it's hard to quantify if the imputation process, the quality of the imputation process will be reliable enough. This goes back into the data processing part, and I'd say having a descriptive analysis first on your data sets prior to even going into the imputation process would be good, and then reanalyzing the imputation process on itself. So it's not just a one-shot thing, right? And the other question that was raised is how can we rely on NOAA GPM or trim data for the processing that we have. So I am not an expert on all the resources that they give. I know that they do give highly reliable data sets, but it all depends also on the data that you're trying to get. So the resolution that you're getting it, the information that you're getting from over there. So processing part, well, using some of the tools that we were mentioning right now, going through some statistics, probably some resampling as well, would be good. But again, it depends on what data you're getting, right? What information you're getting it from and for. I think we can go into the process again. Let me see. If there is any other questions, please let me know right now. I don't know if you can hear me, by the way. Let me put my phones again. That's better. If you guys can hear me, can you just say hello or put in the chat? Good, perfect. So we're gonna go back into the, I'm gonna share my screen. Here they go. So someone also asks about sharing the slides before, and we will do that for tomorrow. I think what I wanted to for the session was, have this back and forth. But if it's better for everyone to just have this prior to, that we can also do that too, of course. I want to, before we start with the whole VS Code part, which is it's not going to be lengthy, but still I want to make sure that everyone understands what's happening. I want to go back into some of the resources that we were sharing yesterday. We were talking about the some online tools for quick visualization before you get your data. You have, for instance, a GeoTIFF or an HDF5. I didn't find any good visualizations for NetCDF aside from, you download something and you put it in your computer or Python or something similar to this. But I found very interesting sites that you can take a look. So one of them is this GeoTIFF. This one in particular is loading a GeoTIFF file that contains some data surrounding this area in Chicago. And you can just visualize your TIFF file prior to performing any analysis. If, see, okay, maybe I need to do a little bit of resampling. Perhaps I need another kind of data sets. So that's quick and easy to do, right? And the HDF5 file yesterday, and we're going to be using this one in the afternoon, or maybe a little bit before the afternoon. The file is containing a grid system. And, this is running on, and I'm going to be talking about the technologies as well that we're trying to leverage in the lab, in the tools that we develop for bringing a lot of the power to the web. And this particular site, this particular information system is using something called WebAssembly, that a lot of the packages and a lot of the data sources and code that has been written to understand, parse, and transform the data that is largely used, gridded files or perhaps large-scale files also. They are written in C, C++, sometimes Fortran, even sometimes Python, of course. And all of these are completely reliable, amazing. But now there is a way to bring them into the web, which is with this standard called WebAssembly. So this is a good example of how you do that. They have a WebAssembly layer that is written in C++, or I think in C or C++, I don't remember correctly, but it's parsing the HDF5 file so that you can extract a quick visualization for your decision making. So this one is an HHR file that I had somewhere in my laptop, which what I wanted to show you is, okay, I have some time boundaries. Maybe I can explore a little bit of what those time boundaries look like. The lat longs scores, precipitation files for the domain of interest. If I have some errors as well, they can be quantified in here. And this is from the format itself. So of course, it's helpful to have a format that's telling you all this information. However, having this sort of request is very easy too. So those are the two things that I wanted to show you yesterday that I didn't have a good example to show, but I think today it's a little bit easier. So let's go ahead and start with the process of the VS Code before we discuss what, oh yeah, I have the Google Earth Engine that I wanted to introduce as well. So all of these tools that I'm sharing, by the way, and I'm showcasing, of course, we're centering on the Hydro Suite for the web page, but these are tools that are available if you have a particular data set that you want to process, that you want to analyze, and you have a pipeline that you already understand, integrating some of the tools that we're using, plus the pipeline that you're trying to utilize is going to be great for the capstone. And of course, this is for the capstone folks. And so consider this information for the next days moving forward, right? Okay, so VS Code. I'm not going to introduce VS Code as what it is. I think it's just a coding editor. So I don't know how many of you use or can you quickly write what is your editor of preference? Some people use Sublime, some people use the Python, some Python scripts as well, some visualization software, sorry. Google Colab, that works too. I like VS Code because you can deploy something fairly easily for web development. You can create applications for web development also, and that is pretty neat. And I'm going to show the integration of Hydrolang right now. So how would you go ahead and you have your, let me show you, you have this one, right? The Hydrolang training. You go ahead and go into data visualization deck. Open Sandbox. I'm going to download this. Okay. So I want to download all of this. Let's see. We export it. Return file. Okay, doesn't want to download. I'm going to show you another way of doing it too. New file. I want to create a my file, my index.html. And I'm going to save it in my downloads, for instance, examples. So in VS Code, what's neat about it is that you have a good way of moving things around. You can export and import software, files and folders. So if you have a particular folder structure that we would like to use, you can do that fairly quickly. I'm going to go in here in my index.html and as we mentioned yesterday, web applications are driven by three different things: the styler, the HTML, which is this, and the logic. The logic is being done by JavaScript. Styling is being done by cascading style sheets, which is CSS. And HTML is just the building blocks that allow you to put the code where you want it to be, right? So in here in VS Code, how do I even start? Well, if you click, I'm in a Windows computer, so if I click Shift, what's that? Yeah, this symbol, and then I click the tab, it gives me this scaffolding. So the scaffolding contains all of what it's required already for my HTML document to work. What do I need is this XML format of doc.html, the language, headers that are saying, okay, this is the particular formatting that I'm using for my strings, numbers, whatever. I have a viewport, the device that I'm rendering this, and Oh, thank you so much, Sergio. I'm so sorry. I'm gonna create a new share screen. Okay, I thought I was sharing the screen. So you're sharing, you guys can see now? Yes, perfect. Thank you. Thank you so much. So I think I'm gonna start again. Going to delete this document. That we can do it fairly quickly. So delete. And in the folder that I had selected before, where I have all the information from the VS Code, I'm going to create an index.html. So I'm just going to say index.html. Right. And in index.html, I'm going to click Shift, this button, met abbreviation it's called. And then I click Tab, and it gives me all of the structure, which is already what I need for my web page to work. And I can say this is my first HTML page. If you have not installed VS Code before, you probably would, it's a little bit to handle with, but what's good about it is that there's a lot of community support. There's a lot of information out there, and particularly tools, interpreters for all of the programming languages that you have. This is supported by the Microsoft Foundation, so they give a lot of push towards having reliability on the tools they're using, and using that idea, I'm going to show you how to deploy your first web page. So if you go the interface that you're going to be seeing is probably going to have this four or five tabs. You go into extensions. There's a lot of installing extensions over there. You can install Jupyter notebooks for interpreting, for it feeds through abbreviations code, and you can even integrate a little bit of AI into it too. So that's going to be helpful. If I click live server, I already have it installed, but live server, and then there's an installation button right here, and it allows you to launch a local server. And probably a lot of us do not have the experience of what is a server, what is this. The only thing that you need to know is it's a space in your website, in your web browser, that the computer knows it can deploy the information towards. Yeah. So once that's installed, go back into my index.html, and it's going to appear right here. You click run live server. It's going to take some time, and afterwards, it's just going to pop up somewhere. And this is how it looks like. So what the good part of this is, we can create also changes on your VS Code right here, say inside the body tags, right? My name is Carlos, and this is WaterSoftHack2024. So once I make a change and I go back into my site, if I save this, oh, sorry. It's this guy right here. If I save and I go back into my site, it's going to appear like that. So how do I then use Hydrolang? It's exactly the same as what we did before in the case studies. So I'm going to close the case study, and I'm going to go into the data module, data, and I'm going to inside this space where inside the website with the tutorial, you go into index.html, and copy paste this.
Carlos, there is
Yes.
a comment in the chat.
Oh, yes.
Could you address it? Thank you.
Oh, yes. I about the VS Code window. Is that what you mean?
Yes.
Yes. We already corrected that one.
Okay, great. Thank
Yes.
you.
Thank you. So again, in here, you are in data. Don't mind about this right now. I'm going to show you how to do exactly this back in the VS Code. Copy this script, copy this line, just copy paste, copy. And then you go into the HTML, and it has to be in here in the head. So I can explain a little bit what that is. And save. So once I save that, and I don't know what's happening. I don't know if Hydrolang is already available. It is available because the HTML page makes a request to the CDN server, to the content delivery network server that contains the Hydrolang package, and it's unloading it into my web application, right? I will not be able to use it right now because I need to instantiate it first, just as in Python, when you have a class, you have to create an instance of the class. It's exactly the same with Hydrolang. So what I'm going to do in here is I'm going to create a script tag, script. There you go, for a while. So I'll say const hydro equals new Hydrolang. And I'll just save it, go back into my website, and I'll open the console. So I don't know how many of you are familiar with what the console is in a web application. It's basically a space in which you can develop your code without having to go back into the HTML. So you can quickly do mathematical operations there. You can use Hydrolang there. You don't have to create a full web application. Just here, it does need to be served. So the JavaScript does need to be served. But once you have that script tag on top, and that works for the other libraries as well, not particularly for the Hydro Compute, because that one has some other features too. But for any other application that you want to run, just put in the script tag. It's going to deliver that library into your application, and then afterwards you're going to be able to use it. So how do you do that? Right click, inspect, and this is going to open this big window. And this big window is just basically what the structure of the site is. So you can take a look. I'm using Edge in here, but it should work in Chrome. It should work in any of the other available browsers. So if I go into the console, so I'm going to explore a little bit of what this is. You have the elements. Elements is basically what the interpreter of the web browser is understanding from what you put in your HTML. So basically, this is a copy of the HTML. If you expand on this, and you expand on this, you're going to see the header, the script that we just called. This is being called by Hydrolang, which is the Google Charts API. So once this is unloaded, and once I declare it in the HTML, Hydrolang is going to call different dependencies that it has and make them available for you. And everything else is just made so that you can utilize the available tools, right? So if I go into the console is my interpreter, my JavaScript interpreter, and it is very friendly. And by that, I mean, it's going to tell you that what you wrote is wrong, but it's going to tell you a little bit of why. And it's not going to break. It's very hard for you to break unless you're doing something like running out of memory, but it's a good place so that you can start writing some and typing some data, and having some hands-on experience on your information. So I'll say, okay, const car equals I don't know. No, I'm going to start with hydro. So hydro, if I call hydro, this is the variable that I declare in the web application right here. So I called it hydro. And now I have it available as an object that contains all the modules available. And perhaps this is a little bit easier to see if you're testing out, okay, what is this library all about, or the other libraries that we're going to be talking about. So you have data with all the examples. If you click on some of them, it's going to tell you, okay, this is a function. How do you call it? The retrieval function, that's the one that we've been using quite a while. What does that look like? There is all the tools for analysis. So this might be a good time for introducing the analytical tools from Hydroline. If you click on them, analysis contains a lot of different functions for statistics, for transformations, for the process of data cleaning, sorting as well. So removing outliers, leaving outliers, for choices, getting mean, max, median. There's some distributions as well that you can apply to your data sets. And a lot of different tools that we can talk a little bit further in the hands-on. But also some map layers too, which is this for tomorrow, the visualization part too, and data, right? The different ways of calling. So I want to show you what's happening whenever you're making a data call, like we were doing in here. There's something in the chat, give me a sec. The code from USCO, I think I missed some parts and I'm having some errors, failed to load resource. Sure. Do you want me to put, okay. What is the load resource that's telling you? Server. Okay, so probably it's not serving the HTML. The live server part is probably not serving the HTML. If you want, we can stay for another 10 minutes after the break, so we can talk a little bit further about this. But yeah, I can share this sample website, this sample web page too. Just make sure, and whenever that happens, is where is it that you're deploying it to? So I'm inside the web application on the HTML, and in the HTML, I went ahead and click on the port, serving the port, right? So if I click back on it, it's closing it, and if I go into my site, it's not there anymore. So just make sure that you're inside the HTML page. You go into Go Live Server, and then afterwards it's going to be available over there. Okay. So what I was going to show you now is this part of the data retrieval process. So we went and talked about this yesterday. So this is nothing new. I'm just going to copy paste. So in the websites, you can copy paste the code by clicking it here, and I'll put it in the HTML. in the console, sorry. So if I click this, going to work. So I'll go ahead and click in this one too, USCS daily values, enter. This is the indentation is not a problem in JavaScript unless you are using tabs. So you can just put it with the different spaces. It's going to understand. And I'm going to click on this one too. Now, when I click on this one, did you see that? Maybe you didn't have the chance to see that. It took, less than a second to get the data, the available data from the available stations. So what it did was, if I go into the network, this is where the data is being sent. I think I showed this yesterday in the VS as well. This is the response. This is the submission for the request. This is the response, right? So now you are able to modify and get and see if the data that you have available from your from the data source that you want to utilize is good or not. You can just test it out directly in your web browser. And if you want to make any changes or you want to separate things in a different space, you can do it because file systems, right? The file system sometimes is a little bit Yankee. So if you want to separate things into different files, you can do it in here. And I'm going to call this my first JavaScript. Oh no, I'm just gonna get my app.js. And instead of coding in here, this hydroland. Wait, there's a question, sorry. How are we going to connect with our server in project level? I don't understand the question. Do you mean how are you going to deploy the application that you're going to create or the visualization and everything else? Well, there are different options. The one that would be easier for you would have the spacing here in the code sandbox environment. And so you do the local deployment, you do the local development, right? You write your HTML. And then in the code sandbox or any other, I think I have 8 minutes. I'm going to introduce the other one too. Because the good thing about the web is that there's many products that are doing exactly the same stuff. So it's easy for you to have an option and not just stick to one of the tools. So you can deploy something in here by uploading files. So you would just upload the data processing that you did. Say that you wanted to process data in Python, you output that as a CSV, you want to visualize that, and you know that you can put that information in a nice map using Hydrolang. So you can just upload that data and put it in here inside the sandbox environment. And before going in deep on this, because it's very simple, it's exactly the same. You just upload the files. When you click in here and upload, is there something? You can create folders and whatever. But I'm going to show you the other one, which is StackBlitz. Okay. Here's another question. Not yet. So this is another resource, StackBlitz. It does the same. And what's good about it is, again, it's free. You can have multiple projects there. You can test out your applications. There is a server for yourself inside of here that is doing the same as the live server in your local environment. You can upload data to, You can download the projects. I find it a little bit, there are some features about this particular environment that I like in comparison with the other one, but the other one is exactly as good. So it just depends on what you want to use as your server deployment. You can also deploy some servers in Python, but I'm not going to be covering that now. We're going to be covering the JavaScript side. And we want to deploy the data sets and visualization plan. We're going to use local server with Highline. So you can use the local server and show that, or you can put it inside of here too. I'd say put it inside of here to see if it works. Okay, good. Any other questions about the development environments? Okay. So what was I showing now? I'm going to be showing this. This is the HydroCompute. This is the second library that we're going to be covering during this tutorial for the tools that you can utilize. So far, as you can see, VS Code, again, it's not just for the JavaScript part. It's not just for the development. You can install Python in here. You can run Google, what's it called? The library, oh my God. You know, the Google Colab, the option that they have for running cells, you can do it in here too. I use it for that kind of development too. It's fairly straightforward. And so just showing you tools that you can utilize for the development. Now, we are 4 minutes from the break. So after the break, I'm going to go deep into the analysis part. Particularly, I'm going to start with the data that I shared before of the WaterSoftHack, this one. Class 2, sorry. Let's see. So please make sure that you take a look and see if what it's there is understandable before. I'm going to share the slides with the WaterSoftHack team so that we can upload them. And it's gonna be now or it's gonna be afterwards, but it's gonna be available today. Okay, so questions before I stop my sharing. The message channel closed before it's been received. What am I doing wrong? Galina, if you want, we can save for the next 5 minutes. And I can take a look at what the error that you have. Okay, perfect. Okay, so I'll stop my share and I will be seeing you guys in an hour. Have a good lunch. There you go. Okay, guys, so we are in the hands-on experience for the next, let's say 55 minutes. We'll try to wrap up at least 2 minutes before the hour, so we have some time for closing and everything. So let's get started. I want to first show you, let me share my screen. Share screen, there you go. Go into There you go. So we were talking about the utilization of different libraries, different programming languages as well on the approaches that we were mentioning before. And what I want to debrief now is on, before going back into the use of the computational library that I want to introduce today, and perhaps the other one as well, the large data streaming one. I know a lot of you are more familiar with Python, so in facing that and understanding that you might be a little bit more comfortable in manipulating information over there, I wanted to share some examples of how you would read HDF5, netcdf files on Python. So first thing to mention is I'm using Google Colab right now, and I'm sharing some data sets with you, some example data sets with you, so you can take a look, interface, and see what the libraries that we're using, or the libraries that you can use in Python for getting information from this type of files. And I have two examples. This is the first one, which is the HDF5 and netcdf files. I'm not going to extract any data particularly. I just want to visualize it, and from there expose you to these different libraries. How do you communicate with them? What can you get from this data? Putting all of this in a data frame, from the data frame, saving it into a CSV. For further processing is a secondary step. What I wanted to show you before is the you have this big file that you don't know where to how to analyze, and so how can we do that rapidly? Correct. So Google Colab, if you're not familiar with Google Colab, is this once you have a Google account, you're able to create different type of files. And the main idea of Colab is that you have a Jupyter notebook that you can share information through fairly quickly. So if you do not have a package, there's many different packages already available in Colab that you can call in through the import statements. However, sometimes if there's particular packages that well, are not as used, as not being popular, but not as used commonly, then you have to install it. You can install it just as with any other package that you need using pip. You do it this way. We didn't have the netcdf installation command here available for obtaining this particular class from the library, so install it afterwards. I call in the h5py, which is the HDF5 reader that enables me to both read, write HDF5 files. Something about the Colab environment is that since everything is online, you can grab your files from the local development environment, and then you can post them up in your Google Drive. And in the Google Drive, you have to, I'm going to show you right now. Let me just refresh. At least this is the pipeline that I utilize, right? Control-click, Control-Enter to install the dependencies. So once that's mounting, once that's done, it's going to refresh and give me this messages. And on the meantime, what I'm going to do is I'm going to go in here into files. In files, you're going to see this mount or on-mount drive folder. So you want to mount your drive. Once that's done, it's going to ask you for permission. And once you have the permission, you can go in here where your dataset is at. And we're, you know, it's basically reading data, right? So reading data, I need the location of where the data is, and use a folders file system to provide the source route that the program has to read the data from. So I created a document folder inside the shareable folder that has both the HDF5 and the NetCDF file. And what I do is I just copy here the path. So this is the HDF5, yeah, so I copy path. And I'm gonna click run on this one so I can import those functions. And I just put this in here, the file, right? So once that's done, you have the library through this object, the library object through this function file, you're able to read, and you just pass the file name and the read option. If you want to write an HDF5 file, then you put the W. You can look into the documentation of HDF5. In fact, you can, I think if hover, there you go. If you hover over each of them, it's gonna tell you exactly what, it's gonna take you to the source, or you can read more of the documentation of each of the packages. So with that, I know that the HDF5 files have keys. So I want to print all the keys that are available. And from there, I want to group these keys in a list. So the first item within this list, I want to put them within this object, sorry, I want to put it in a list. And I want to access the group key. So the group key that I just extracted, I want to access it from the file. So the file HDF, this one that I'm reading from the binary. Then I want to print all the data sets in that group. So group key, which is this object here containing the values of keys from the list and the list itself. And then it's just printing of the data sets so I can take a look of what it has. This is exactly the same one as the one that I showed here. So it's a neat, great way to quickly visualize the information. And then from then onwards, extracting the data will depend on the particular variable that you're interested in, correct? So this file has precipitation, calibrated, uncalibrated errors. There is Kalman filter weight ring here, probability of liquid precipitation, quality indexes, and all of that is coming from the file itself. So I'm not gonna go into extracting anything just yet because the idea is showing you one way of interfacing with that file. And similarly with the NetCDF, I have the NetCDF file right here. This is from a NASA, I think it's in the Arctic, a NASA Arctic file, a NetCDF collection that has many different variables. And so I wanted to see, okay, how can I do this in Python? Well, similarly, copy paste the file path. After the file path, I use the dataset function that I got from the library of NetCDF. And if you want to take a look into that, I think, yeah, well, there's more functionality there. There's more documentation about each of them right here. And I know that the NetCDF files, the variables can be stored, are stored, sorry, with this structured data set, the variables, the keys. So I pass this and I want to get this dictionary. So I want to read all of what is available there. There's a lot of information. Accessing a particular variable. So in here, temperature, I don't have any temperature, but I want to access the time variable. So I just pass the variable time. And it's basically a dictionary, right? So you just pass in the string that you want to access, pass in those names, and afterwards it's going to be given to you. And then you can extract this information and put it into a data frame and for further processing. But this is the very base use case. I'm sure this is just an example. Again, if you would you have high processing computing, you have 50 gigabytes of an LTDF file that you want to extract information from, you're not going to be doing it in your drive. You can use exactly the same commands, but you're probably going to need another environment, either your local PC or you put it in HPC. There are, depending on the institution where you are, there are different ways of accessing a nice UI from Python environment. So I will move to the second example, which is more on the hands-on of the USGS station that we had yesterday. We had already downloaded the data. And let me see, which is this one, example 1, example 2, data cleaning, okay. So everything is in here. I'm not going to rerun it because I'm just going to explain what we did. This is what we had yesterday. Make the request, have pandas for putting in data frame, and have matplotlib for plotting quickly and visualizing this on screen, right? Make the request, you have your particular site, the formats, the time, the start time, and end time. So you make the request. After you make the request, you get a response into an object. This response you convert into a JSON. The JSON afterwards is clean. And by clean, I mean you don't need all the metadata over there. You just want the values of the time series. That is the time and the time and the value itself. So that's exactly what we're doing here. And for we create data frame utilizing the dates entry and the values entry. And with that, it's very easy to just create a quick chart. And the quick chart, you can customize this as you want, just to visualize this. Now, this particular subset for this station is, you can see from 1900s to 2020, there's quite a large span, and probably the values that we're getting are not as often in the beginning of the recording period. So you can see it in here. In the beginning, there is a big jump until the next data sets, and big jumps and big jumps. But then as we're moving forward in space, in time, this recording are becoming better. That makes a lot of sense, right? From 1900s to 2020, 2024, when I have more information. But it'd be interesting if we can standardize this and normalize it so we can visualize it a little bit better. And that's exactly what we do. There is a library that is commonly used for data processing, particularly for machine learning, called sklearn. They have a lot of pre-processing algorithms that are fairly straightforward to implement. And within these algorithms, you have the basic mean, max, scalars, the normalizing objects, identifying if there is any issues with the data. So I would suggest, again, take a look into the processing libraries that you feel would be a little bit fitter to your use case, and just go ahead and try them out. So what I did is I got the standard scalar and the min max scalar, which was, those were the main one of the main processes that we were mentioning in the beginning in the morning. So you define that because both of them are functions, are classes, sorry. And so you append that to a variable. You call that variable afterwards as a function that has an object. So the scalar in here, I use it down. There are many different, I think you can get something from the scalar. If I hover over it, no, I can't. There are multiple different functions that you can extract from there. I'm using the fit transform, so I'm transforming this shape to be between -1 and 1. So I can standardize the flow rate. So you pass the value, and afterwards, I just append it into a new column in my data frame, right? And I do the same with the normalized flow rate. I use the min-max scaler in here, fit transform, use the same values, and reshape it into -1 and 1. So this is how it looks like. I have my values are looking like this, but the normalized and the standardized flow rates are in this. So what we said before was if it's very much negative, very much positive, you need to evaluate for your use case. Something that is very interesting now with the whole AI implementations, there's added features that you can extract from tables. For instance, in this table, I'm not running it right now, but I want to just show you. I'm going to call in this libraries, and while this is running, you can get quickly distribution that might fit within your data, to the distributions as well, time series suggestions that tell you, okay, perhaps this is how your time series looks like. And it's, it takes a second or two to do this. So that's pretty nice. I'm going to go and click on this one too, so you can take a look. And this is, I'm not really sure if it's another feature that you can add. Probably this is a feature that you can also add in VS Code or any other developing environments. But I know that for the Google stuff, they have their own library implementations that they like to add into their tools. So once I do this, I call the data frame by just right-clicking on it, and you can see generate code or see suggested charts or other data frame interactive tables. So if I click in this one, it shows me some suggestions. And what do I do with those suggestions? Well, I'm able to further get more insights from the data. So those are the examples that I have for today's discussion with Python before we move to the next step. Any questions so far? I see there's one. Standard of supposed to change the area because this code. What is the difference between using JavaScript and Python for external data? Galina, let me read yours first. Yes. They are supposed to be different because what it's doing is you have all the variability you can see in here is between 4201 or so. And then there is a high almost at 42. This is very regular. It's a stream flow site. So, it's just varying a few feet within 10 of the 4200s. So what you want is that the scale is going to be minimized, right? So by saying the range -1 to 1, it's going to transform this into a smaller space. So that's one question. The other one is, okay, differences. So the difference between JavaScript and Python is negligible depending on what you're trying to do. The implementation of a function, if I'm doing the normalizing of a function in Python, is basically going to be the same as in JavaScript because the function itself is just written in different languages, right? Now, JavaScript is fairly fast because it's being parsed on the go. So once I type something, the compiler is doing something called just-in-time. It is a just-in-time compiler. So it's running right as I am typing things. And that makes it really fast. Now, what is the difference between Python and JavaScript is you can do a lot of data overhead. So you have large scale data overheads in Python that you cannot do directly on the browser. Why is that? Is because well, there is a big adoption for the scientific community to move towards R and Python, and you can deploy in HPC systems your scripts that can be run over there. You can also do that with Node, but traditionally Node is more for the interface part, right? So if you were to look at the source code of just this page, all of this is JavaScript as well, but in the backend, you're sending requests to a server. The server is running and crunching the numbers, and afterwards you're getting that back. Google is very generous at offering this kind of stuff for the public, so that's great. But in large scale systems, you probably use a lot of Python for the development. Now, what I'm going to show you now is that you can do a lot with JavaScript too, because the browser has become quite powerful in many different ways. There's another question. Standardizing, normalized assets. How is this tool? Can you brief them? Standardizing -1 and when and how we use this tool. Can you brief them? So you will need to go ahead and take a look at what the data looks like. So I think there's some values -2. It says -2 is probably saying, well, I'm getting some not extreme values. It's not going to, I'm not going to call extreme values, but definitely way lower than I would expect from the traditional trend that I looked into the data. So what I would do afterwards is probably apply some seasonality to this data set, some trend analysis to these data sets, right? That is answering one of the questions on the question and answers in the webinar chat. The standardizing and normalizing is two different ways of just visualizing the data. If you have a lot of variability, by creating a smaller subset, what you're trying to see is, okay, I have an issue with my data, or do I need to remove some information from over there or not? Right now, I'm not going to get into we need to remove this or not, because I want to go into the other tools. However, you can take a further look by plotting this. If you show this part, if you, I'm going to select one of these ones, each of them, any of them. So once you select this, and this is using something else, this is AI generated code, by the way, and you say, okay, add cell, and I run this cell. It's using the standardized flow rate. It's giving me a little bit of a different outlook than before. And from there, I would say, okay, I'm going to move to a next step, right? There's another question in the, give me a sec. That RTL process explain a Hydroline using JavaScript that we did yesterday at Sandbox. So that is the same as that RTL process in Python. Whose code is available in Drive? I did not understand the question, sorry. So you're saying that it is the same exactly, yeah? So it's just that one of them is Python, one of them is JavaScript. I was showing you because a lot of you are more familiar with the JavaScript part, with the Python part, so I want to show you how to do it in Python, but the main purpose is show you how to do it in JavaScript. And the code that is available over there, it's, yeah, you can use it, you can modify it to the best of your ability if you want. And actually, I would suggest further improve it, further take a look at different algorithms that can be applied for the trending analysis. Any other questions? Okay, if not, then I'm going to move towards the explanation of the other library that I had that is called the Hydro Compute. Oh, okay. There's another question. Says, could you explain how you wrote that URL part? Okay, the URL part. So for the Python script, you mean, right? I think I'll explain the two, the Python and the JavaScript version. So for the Python, I declare these variables in here because I am interested in the site in this number, 10,000, correct? And I want it in JSON format, and I know my start and end date. So what I want to do is I know that I want to connect to USGS daily values. I know that this site exists over there, and I know I'm not really sure what the start and end date are for the data sets that they have, but I am interested in getting data from 1900s to 2023, correct? So what do? I copy the URL that I'm supposed to make a query to, and I put this, and in Python, just as you can do this in JavaScript as well, you can do it in C, C++, you have the option of parsing a string. So all of this is a string, and just append options at particular locations within the string. So the options that I need are the format. So this is this part, format, the site, and the start and end date. What does the URL require? The basic URL for making a request is this. After the question mark, you start appending all of what the URL of the REST API is asking for. So you put the format in here, you put the site, and you separate it by and so on and so forth. The way we do with Hydrolang is different because in Hydrolang is it's the second one. I do not need to declare the URL because the URL is already saved in the data source space that Hydrolang is going to look for. The only thing that I need to tell it is, hey, go look at USDS at the daily values data type because I need that URL. And in that, once you find the URL, append all of these attributes into that URL and made the request. So that's exactly how it's done. That's once you have the string in here, you utilize the requests library through the get function. You append the URL, then you wait for that data to come back. So if I am going to run this one and I want you to take a look, that there is a little delay happening here. There you go. So send a request, delay, and afterwards, once the data came back, it's transformed into JSON. And then the other question that was asked is, okay, Siriana, I'm going to come back to you just in a sec because there's a question of the value being plotted. So I already know this data, right? So because it's this example that I have in here. Is the example that I have in here. I know that once I get the data has a lot of meta information that I don't really need. And I can show you that. Let me go to main. And I'm going to copy paste this. Copy. So that you take a look before plotting anything. So I'm going to comment this. You comment in JavaScript by using the symbols. And in here, I'm going to push USGS stations. It doesn't like it, and it tells me, hey, I don't know what you're trying to do. USGS data. Oops, did a mistake. Give me a sec, please. Okay, so, and here is already transforming the data for me because I passed this transform true option, but I'm going to remove it as well. If I click refresh, give it a second, please. Refresh, and now. What you're going to get is a JSON object that looks like this. What do I need this JSON object for? Of course, getting the metadata, but in particular, what I'm interested in is in the values. So how do I do that? I'm going to go back into the Python example. The Python example, what you do is the data has an attribute called value, and inside that attribute, it has an attribute called time series. Inside of that, the first element that I have is this values object, and the first element of that particular value is this values object is the value of the time series. And similarly for the date time. So this is just a notation for a for loop extracting the date time for that particularly time series object that I have, which looks like this. I don't know if I answered your question already. And okay, I have the question from Siliani. Okay, you visualize the data, how we go about formatting for visual graphs. We're going to be talking about that tomorrow. Using both the JavaScript libraries and the Python libraries too. Another question, what if you need several USCS stations at once? You need to create several URLs for each. Can you do it in a batch? You can do it in a batch. So the good thing is you can generalize this. If you're doing it in Python, you can generalize this by creating a for loop, a little batch that just searches for the specific site. Or as the example that we did yesterday with Hydroline, in which I was just making a request for each of the stations. So I get all the stations, and afterwards I just click on them, and I get that data back. But you can just, the station name, and the order as well. So you just make an array, and just for each of them, you send a request and a request and a request, and then you save it. Either if you're using Python in a data frame, you're using Hydroline, you can use it in a big array, and afterwards download it as a CSV. Any other questions? Okay, so I'm going to move into the library that I was going to cover right now. I think we got a little bit over time, but I'll try to speed it up. So close. If you have any more questions, please let me know. I'm going to be checking up on the side too. Okay. So we saw yesterday about Hydrolang. Hydrolang it has a lot of functionalities. It has functions for statistics, a lot of statistics. Once you get your data, for instance, you can get the descriptive statistics to tell you about what the data looks like. There are several functions. There's a particular function called basic stats, in which you pass the object where your data is being saved, and then afterwards it's going to tell you the basic stats for that data. What you're going to get is a big array, and then this array can be formatted into a table, and you can just use another function called table for visualizing that data. But you get number of values, minimum, maximum, sum, mean, median, all of that stuff. A lot of the functions that are available in these big libraries for scientific computing in Python. Many of them are already in Hydroline. Now, one of the biggest and hindering issues that are with the web development is particularly with the browser rendering is that the browser runs in a single thread. So a single thread means you need to finish an instruction to get to the next one, to get to the next one. So whenever I'm doing this, the responsiveness of the browser is telling it, hey, pay attention to any time that he's moving the rolling screen, right? Before completing any other task. But there are many ways in which you can supersede that by utilizing the multi-threading available in your device. I'm not even just saying laptop, in your device. So that's where the HydroCompute library comes along. So HydroCompute is this multi-threading library in which it doesn't have to do anything in particular with hydrology. You can utilize it for different things. But the main purpose is I want to run complex analysis on the browser so that I can remove a lot of the overhead sending requests to a server when I can already do it in the browser, right? So just to show you, this is how it looks. There's different technologies that come along in play. We're using the GPU and the CPU threading environments for running an instruction. An instruction has a particular format, and I'm not going to go into all of them. I'm just going to show you the high level of what we're trying to achieve with this library, which is particular way of interfacing with data. So I know that, I'm just throwing you in the pool right now. We didn't know JavaScript. We're kind of getting familiar to it. Now we're doing something a little bit more complex. But in reality, what we're trying to do is give you all these tools so that you can have like a comprehensive tool set in your hand, right? Rely on Python, great. Rely on JavaScript as well, because you can do a lot of these powerful tools and combinations. So we have implemented this library so that it can run on the GPU and the CPU. The way we did it was through using array buffers. An array buffer is just a memory instruction. So instead of, say that I have an array of 1, 2, 3, 4, 5, that array is allocated in my physical memory as an address and as stack of memory. But I can move that around. And then what I do is I take it from the main thread where all of this visual manipulation is being done. And then I submit it into all the separate threads that are not being run, that are not being used by the browser, or particularly from my computer. Of course, this is way much more complex than what I'm explaining. There are multiple different threads and instructions running all the time. But at a particular subset of time, I'm able to grab this data and do something with the data. By doing something is I have a function. A good example is I have a Fibonacci series on data. I want to get Fibonacci to 10, Fibonacci to 15. And instead of doing it in the main, I do it in the separate, okay? I'm not gonna go into details about that in particular. I'm gonna show you some examples. So the way you run these instructions is by, we have a task scheduler as well. And the task scheduler, what it does is you can run multiple tasks starting at time 0, and then starting at time 1 that are dependent on time 0, and so on and so forth. So think about how in a hydrological system, there's rainfall, first runoff starts at time 0, next, the runoff at the next location depends on the runoff on the first location. So that means that there is a dependency coming from behind. And the way we did it with the library is very simple. We said, okay, and this is an example of how that looks like. We have multiple functions available, and I'm going to be talking about how you declare the functions, how to use the functions. This is not a library for that contains function. It has many examples, yes, but it's a library that can utilize the function that you declare so that you can run it on the back. So we have some ARIMA processes, a detrending function, a Monte Carlo simulation, and then this is a repetition because we wanted to test out for randomly generated data. So 1 million points between 1 and 100. I'm going to try it out and see how that will run and do exactly the same, but each of them depending on the output of another. So the output of this is the input of this, and so on and so forth. And if you have multiple arrays, so you have multiple functions that want to run at the same time, you just declare it by using different array structures. So what's the idea of the library is you remove a lot of the overhead of how you compute something. So the best example, and I know this is generic examples, you can go ahead and take a look on all of them if you want. But the exercise that we did yesterday with Hydroline, in which I just had like a visualization deck of streamflow for the USGS stations, I want to grab that data and I want to apply some statistics to it for doing some basic prediction, some basic model. And if I want to do all of that in the browser, so this is the first example, right? You guys remember, click on one of these, retrieve data, and if there is any data there, it's going to grab it. If there's any data, nothing's going to appear. I use Morgan, East Canyon. This one does have, right? Tells you all the statistics and whatnot. But we improved this so that we have a separate multi-threading environment where I'm able to not only visualize the raw data, but create some basic prediction to give me an idea of what might happen, or applying some more than usual computationally expensive task on the same data. So all of this is just scaffolding. It's just how you append some of the tasks there, but the main focus is in here. We are relying on 3 different technologies. The first one is called WebAssembly. I think I introduced WebAssembly briefly before. WebAssembly is this standard that allows me to create, to compile code from C, C++, Fortran, and other functions and other languages. Sadly, not Python so much yet. And put them in a binary format, and then I can use those functions into my web applications. Why is this important? Because web applications have an overhead. The fact that I'm able to run and use the UI and have a responsive Netflix documentary running in the background, that has an overhead because of how the compiler has been built. That means that performance-wise, it can be much better. And that's what we're trying to achieve with the WebAssembly standard by using, in the computer science, it's kind of, you can say, it's as close as you can get with the metal. So as close as you can get to the ones and zeros in binary format. You grab that, you put your data there, you perform the analysis that you require, and afterwards you get the result back. So you don't really, the reliability is the function that you're using correct or not correct? Or what is the end purpose of my data sets? Do I need to refeed the data once again, once I have the results? And that's case specific, of course. But what we're using in here is we compile functions from C which are these ones. We also declare functions in JavaScript because you can also, JavaScript is fairly quickly. And if we're running in the background in the multiple threads, it doesn't really need anything else. There's very little overhead. We also have, and I'm not showing anything here because time is not of my, time is running by very quickly. We also have a GPU standard, which is called Web GPU. So I know I'm saying multi-threading and threading a lot, but that's basically what we're trying to do is utilize as much as possible the resources of our devices. So similarly, as you can, you have your multiplayer game, your phone, or in your computer, you can also use that same for creating a computation. And all of that information, you can find it in the GitHub. But the main thing that I want to show for today, at least, is how we improve that use case that we previously shown about the USCS stations. So right now it's waiting for those stations to come here. And we did it by not implementing, but further analyzing the data sets once they came to us, right? I might want to speed this up, so I'm gonna go in here. And by the way, I know that I'm going fairly fast, so any questions, please just put them in the chat, in the Q&A, or send me an email. I can go ahead and take a look with you. It's not so much about getting you lost, it's about exposing you to the tools that are available to your disposal. And, just move around with them. So let's see if this one is working. There you go. Still waiting for that request to come back. And I guess there's something to be said about that. When you're making a request to a server, if there's a server overload, then you might run into waiting much longer than what you want, which is, I think, what's happening to me right now. Probably there's a lot of requests being sent. So I'm just going to wait for a little bit. In the meantime, there is some questions in here in the chat. So there was a question about the GPU in Colab. There is, as with any other language, you can use multi-threading as well in Python, and you can use multi-threading in the GPU. I am not really sure how to do it. Maybe some of the other panelists can, but I'm not sure. Probably there's good documentation for that out there. I can take a look, and afterwards I can let you know if you can do it. Can we add buttons to these HTML lines instead of doing backend? Yes, yes, of course. You can modify the buttons and having more requests there if that's what you want. Oh, there you go. Finally, the response has come back. You can modify the code. It's available out there. It's, right now I'm showing Salt Lake City. I can show you some other locations. And the main purpose is you get more comfortable with HTML. HTML is not that hard to declare. Get more comfortable also with the data pipelines. And yeah. Okay, so the station information came back. So the station looks like this. Is exactly the same as the response before. What did we do is, by the way, this is also fairly well declared, the documentation of the processes that we're taking. So you can take a look into the code once you have some time. I think we used Morgan before. So if I click and retrieve data, let's see. Is there any data there? Okay, no. So I'm gonna go up Weber River. retrieve data. So now the data is being retrieved, and I got my response object already. So I'm going to explain a little bit about this. What just happened is I run all of these functions on the back on this data, and this is the response. And I put them in a graph. So of course, put all of this stuff in a graph that creates overhead, that makes some of the performance get lost. But I'm able to do it. So that's the main purpose of the library, right? That you're able to remove and not do in the same. I like to think about it like cabinet, not put in the same cabinet all the stacks of clothes that I have, but I have multiple cabinets in which I can just put them behind. And you can download data. You can download the simulation information as well. You don't. Someone asked about downloading the data. If you click on download, allow, and the data that I downloaded in here is just this raw data. And I downloaded in CSV format. Again, I'm using HydroLang for doing this. And it's just appending the function to a button, just as someone was asking. Okay, guys, so I think I'm going to stop now. We're supposed to finish a little bit by the hour. So if you have any questions, send me an email. Just go ahead and move around with take a look at the libraries. Also the examples, we can provide some more examples as well. Again, if you have any data sets that you want to explore and that you don't know how to start with, please let us know. We can take a look into that. And I'm just waiting for any questions also for the capstone project. Please let us know. I think I shared it with you guys. No, if I can resend that link into, yes, I can reshare that link right now. Copy access. Okay, I'm gonna stop the sharing. Give me a sec. And I'm gonna go into class. You're probably just going to be able to visualize, at least that's what it's going to say, but you can download the data. So I'm gonna put it in the chat. And no, the access to the drive, you have to set that up. So that's an example that I created. So you can set up your own drive. But if you have a Python script, a Python environment in your development, then you can do it. Okay, guys, so I'll finish right now. I'll see you tomorrow. And thank you so much. I will address this question tomorrow. The Monte Carlo question and what's the part. Thank you.